We come to our last quantity in our study of rotational motion, angular momentum. And in this first video, we'll look at angular momentum of a single particle. And later on, we'll look at angular momentums of whole bodies spinning. For defining a particle, and we'll say particle is right here, mass m, at radius r from some chosen center of rotation or axis of rotation. And we'll give this particle some speed v, so it has a velocity vector v at that instant. The particle has angular velocity. We'll say counterclockwise in our example. We can now define angular momentum. It's given the symbol L. I'm not sure why, but for a particle, single particle, we use lowercase l, and for a solid body, we use capital L. I'm not sure why that is true too. For a single particle, angular momentum is equal to the cross product of first radius cross linear momentum. And this is really the defining formula of angular momentum. We can write this angular momentum equals r p sine phi, where phi is the angle between the radius and the momentum vectors. Now, oftentimes you will not know the momentum. You'll be given the mass and speed of an object, so you'll calculate it. So the most useful equation we have is L, angular momentum, is equal to R mv. Actually, let's take the, let me redo that because we're going to take off the symbol for being a vector. Absolute magnitude of the radius times mass times the velocity's absolute magnitude, which means it's speed, times the sine of phi. This is our most useful working equation. Phi ends up being the angle between the velocity vector, which is the same direction as the momentum vector, and the radius vector. An approximate drawing of what the example here, we have the radius vector is like this, and the velocity vector, make sure you draw these coming out of the same point. Velocity vector is here. In this case, this is a 90-degree angle. One nice thing about looking at this in our first year college class is that most of the examples, almost all of them, you'll see 90 degrees as the angle. And why is that nice? Because the sine of 90 degrees is 1. So, like the case here, we have a right angle here. So we're not going to need to consider this angle too much in this unit. The units of angular momentum will be a position vector, that would be meters, times mass, kilograms, times the speed, meters per second. So it ends up being kilogram meters squared per second. How do we determine the direction of this vector? We curl our hands from the radius vector to the velocity vector or momentum vector, which again is the same direction. Using our right hand, that gives us thumb up. So you would say the direction of this angular momentum vector is up out of the page. We can give that symbol this, which is supposed to be an arrow tip coming at you. Or more easily in this case, definitely, is to use the positive, negative, counterclockwise, positive for counterclockwise, negative for clockwise, and say that since this is counterclockwise, we would give this a positive value. So let's do a simple calculation here and see how an angular momentum calculation turns out. If we use mass 2 kilograms, radius 0.25 meters, and speed 20 meters per second, we will have L, angular momentum, equals RMV sine of phi. And like we already said, this is 90 degrees. So this is all just 1. We have R, I'm assigning it 0.25 meters, times M, I assign that 2 kilograms, times V, which is 20 meters per second, and times 1. All that is 20 times 2 is 40. 1/4 of that is 10. Our unit is kilogram meters squared per second. And we want to give this some direction, so I'll just call it positive because it is spinning in a counterclockwise. Alternatively, you could say it's the direction of the vector is out of the page. So in looking at our basic equation to help us calculate angular momentum, we see for a particle there's 3 basic ways you can increase an object's, at least the magnitude of the object's angular momentum. You can increase the radius, you can increase the mass, you can increase the velocity. Doubling any of those doubles your angular momentum, so they're all direct proportions. Radius, doubling the radius doubles the angular momentum. If you have 2 times the mass, you have a heavier mass, 4 kilograms instead of 2 kilograms, you would have twice the angular momentum. And if we double the speed to 40 meters per second, again, we would double the quantity that is angular momentum. The other thing about angular momentum to look at is this angle, phi. What if phi is not 90 degrees? So the radius vector is always this way, we'll say. So we're considering the particle's position to be the same as in the prior example. But let's say instead of this V here, we'll call this A, B, C. In case A, phi is 90 degrees, so we have L is just equal to RMV. RMV sine 90, RMV times 1, just RMV. In case B, we have, now this phi here, you got to be careful because the radius vector is this way and the velocity or momentum vector is this away. So this ends up being 135 degrees. So L is equal to, it ends up being 0.7 RMV. 0.7 because the sine of 135 degrees is 0.7. In case C, what is our angular momentum in case C? What's the angle? Well, here's our radius vector. Our velocity vector this time would be 180 degrees. The sine of 180 degrees is 0. So in case C, the object has no angular momentum. So when an object is either going toward the center of rotation or away from the center of rotation, it has 0 times RMV, which is of course equal to 0. And another thing to note here is if you look at the relationships here, what angle gives you the greatest angular momentum? This is the same as in the case of torque, where if you want the maximum effectiveness from a force, you want to apply it perpendicularly, the direction perpendicularly to the radius vector. Like if you're torquing on a wrench, obviously you would not want to push toward the center of the nut. That would not do you any good. You want to be at a right angle. In this case, you have maximum angular momentum. It's the same. It's at 90 degrees. And it goes to minimum 0 momentum when you have either 0 degrees or 180 degrees. Thank you for watching all the way to the end. Hopefully this was helpful. In the next video lesson, we will look at angular momentum of a solid spinning object. See you there.